All right, so last time we were looking at warming up some water. What was it, 25 grams, I think? 25.0 milliliters? Or was it 50? It was 50? 50.0 grams of H2O liquid at 25 degrees C. And then we were going to warm that water up to what temperature?
100 degrees.
Okay, so we go 50.0 grams of water at 100 degrees C. And we want to determine the energy change. To determine the energy change, we look at the initial energy and the final energy. This is the internal energy, which we call the total energy. The total energy is comprised of what?
The potential energy.
Yeah, the potential energy, I'll just call it PE initial plus KE. There are different abbreviations for kinetic energy, E sub K or KE. I'll just use KE, it's easier. And so we need the initial potential energy and initial kinetic energy, and the final, we'll need the final potential energy plus the final kinetic energy. The kinetic energy, we can use kinetic molecular theory to determine what that is. And it's going to be directly proportional to the temperature, the absolute temperature. And so the kinetic energy is not difficult to calculate. We have equations, we can calculate that. The problem is with the potential energy. The potential energy of liquid water, what is it? Well, it's going to be all the energy that is contained in that. And what is the energy? There's energy in the hydrogen bonding. You know, to break hydrogen bonds requires energy. To form hydrogen bonds releases energy. And so this is what causes the water molecules to be sticky, is the hydrogen bonding primarily, and London or dispersion forces that hold the water molecules together. And then there's potential energy in the bonds, potential energy in the electrons, et cetera, et cetera. So the potential energy, what did we conclude about the potential energy initially?
Very difficult.
Yeah, very difficult to calculate accurately. You can estimate it, but the errors associated in the calculation. And so we never calculate the absolute internal energy, and we never calculate the absolute final internal energy, initial and final here. But we can calculate, or we can determine a change in internal energy quite accurately. And so delta U, this is no problem. We can do accurate calculations for this. And so delta U is going to equal the change in potential energy, that is potential energy final minus potential energy initial, and the change in the kinetic energy. Was there any change in the potential energy? No, I mean, this is still liquid water. And so that didn't change. And so this is just entirely in terms of kinetic energy. When we have things change in terms of kinetic energy, if there's a change in kinetic energy, then we're looking at the motion. The motion is going to be related to the temperature. And so this change in kinetic energy we call heat. And so when we have an object, this is an object. When objects change energy, they either warm up or they cool down. And that's what we call the heat, is the exchange of kinetic energy here. And that's just going to equal the amount of stuff we have times C times delta T. Usually the amount is in mass, so that's MC delta T, if the amount is in mass. MC delta T. But the amount doesn't have to be in terms of mass. So if we take a look over here, these are C values. If they're in terms of mass, we call it specific heat. Specific heat always is per gram. So this is joules required to heat up 1 gram of whatever substance by 1 degree C. And so for lead, it only takes 0.13 joules to heat up 1 gram of lead by degrees C. In fact, if we look at this table, lead is the smallest amount of energy. Lead and gold are both 0.13, but I'm not sure which one is actually smaller. And so something like lead and gold takes very little energy to warm it up or cool it down. What has the highest specific heat? Hydrogen gas. Hydrogen gas has a very high specific heat, 14.3. It's pretty high. There are things, other things too. H2O liquid. You know, hydrogen gas has been unusual. So we'll just look at H2O liquid. H2O liquid is 4.18, which is pretty high. We consider this high. In fact, H2O liquid has a very high specific heat, meaning it takes a lot of energy to warm it up by degrees C. And so if you put a pot of water on the stove, it's going to take some time. It's got to absorb a lot of heat before the temperature rises. Versus if you put copper. Copper doesn't take much heat, only 0.385 joules to warm up by degrees C. So those are specific heats. And so this we can calculate very accurately. So the delta U, there's no problem. We can determine that accurately. We aren't going to put numbers here at U initial and U final, but we will put numbers here for delta U. And what was the number we calculated last time? How much heat was required to accomplish this here?
15.7 kilojoules.
15.7 kilojoules. Excuse me, did I talk about the sign convention?
I would think so.
Yeah. In this case, it's positive. And so when Q is greater than 0, we call it endothermic. And so it's got to absorb that. If Q is less than 0, that means we're losing heat. So in other words, energy is conserved. So in order to warm up this, it's going to require 15.7, but to cool this water back down, it's going to require removal of 15.7, so it would be negative 15.7 kilojoules to go the opposite way, and that would be XO. And so what we have here is a situation that's like this. There's no such thing as negative 15.7 kilojoules. The negative is just to tell us the direction, you know, whether we lose it or we gain it. It's like a $20 bill. You know, there's no such thing as a negative $20 bill, but you might have negative $20 in your account because it's just the direction of exchange. Energy is the same way. Energy is always positive. We just assign positive and negative to account for if this is losing. Well, if this is losing, something else must gain. And we come up with a statement of the first law that looks like this. You know, we call one thing the system, and then everything else the surroundings. So if the system gained 15.7 kilojoules, that must have come from somewhere. And where it came from is somebody must have lost that. And what lost that is everything else, which we call surroundings. And so if the system's plus 15.7 kilojoules, the surroundings must be minus 15.7 kilojoules. So it's a zero-sum gain. And so this is the first law expressed in a different way here. Well, what lost? Well, you know, we could have some hot water, lots of hot water, maybe warming up the cold water. And so we could have an object cooling down, losing heat. Or we could have a reaction or process. A reaction or process would be like this. Could we heat the liquid water to a temperature greater than 100 degrees C? Not really, because what's going to happen at 100 degrees C?
Boil.
It's going to start to boil. Unless you have a pressure cooker. If you have a pressure cooker, then you can go above. But at normal ambient pressure, it's going to boil. When it boils, when water boils, does the temperature continue to climb, or does the temperature just stay stable? If you put a thermometer in a pot of boiling water, does the temperature continue to increase, or does it stay at 100 degrees C? You know? Oh yeah, it just stays at 100 degrees C, it doesn't change. And so, at the boiling point of water, it's just, the temperature is going to be stable at 100 degrees C. So where's all that energy going into? All that energy is going into the process of boiling. And so the next thing we're looking at is the reaction slash process. Process would be like boiling, melting, freezing, condensation, or reaction. If you look at a chemical reaction, we're thinking we're going to get the energy, this 15.7 kilojoules, by burning methane. And so we start off with methane plus two O2s, and then we're going to form CO2 gas plus two H2O liquids. So we want this to lose, delta U here, we want this to be minus 15.7 kilojoules. That way, this one can lose that 15.7 kilojoules, so this one can absorb that 15.7 kilojoules and increase in temperature. So it doesn't matter which one we call the system or the surroundings, they're just the opposite ends of giving or taking energy. So how much methane do I need to burn for this? The amount of energy that I get is going to depend on how much methane I burn. So I need to figure out how much methane I need to burn. Do I need to burn a full mole? As written here, 1 mole plus 2 moles. Or less than a mole, or maybe more than a mole. I need to know how much. In order to figure out how much, I need something like, I need some additional information. That is, something like delta U combustion. This is how much energy I get. And the typical units for delta U combustion would be in kilojoules per mole. So I got to figure that out. So this is the amount of heat. Now, this is a bit tricky, because usually delta U, this is an intensive property. Intensive means what? Intensive means versus extensive. Intensive means it doesn't change on the amount, right? It's like density. So let's say this were 1,000 kilojoules per mole. If I had 2 moles, does that change the kilojoule to mole ratio? No, I mean, it'd still be 1,000. Even if I had 2 moles, it'd be 2,000, but the kilojoule to mole ratio would be the same. That's intensive. And so intensive is kilojoules per mole. Or it could be intensive, well, that's intensive, sorry. This is intensive. However, I'm expressing this as extensive here. I want 15.7 kilojoules. That's going to depend on the amount here. And so sometimes it's a bit ambiguous. Sometimes we'll express delta U in terms of an extensive property, that is, I want this delta U, the change in internal energy, to be 15.7. Sometimes I'll express the delta U in terms of an intensive property. If I burnt a mole of this methane, how much heat is released? And so there's a bit of ambiguity there. And so to clear up some of that ambiguity, we do something like this. We look at how much heat. How much heat I'm going to get from this reaction, which is going to be Q, is going to equal the amount of methane that I burn times delta U. So when we're looking at an object, Q of an object is going to equal the amount times C times delta T, or MC delta T, if we're using specific heat. If it doesn't have units per gram, then we call it the heat capacity. If it has units per gram, we call it specific heat. Then we have different heat capacities, molar heat capacity, etc. Over here, when we're dealing with a reaction or process, there is no delta T. Because what we do is we start off at 25 degrees C here, and then we end up at 25 degrees C here. In other words, what we end up doing is we just wait. We wait for the temperature to reestablish. So there's a graph here.
I'm confused about the Q equals amount times delta U, because over there on the left, isn't delta U equal to Q?
Mm-hmm.
So how can it be, how can they both be equal?
They aren't. They aren't equal. It depends if you're talking about an object. If you're talking about an object, then this is it. Delta U is equal to Q of the object. Q of the object is either going to warm up or cool down. The object's not going to change. Over here, this is different. This is Q for reaction or process. So we have to use a different Q equation for reactions and processes. And so first off, we have to determine, are we dealing with an object? If we're dealing with an object, then Q's that equation. If we're dealing with a reaction like this chemical reaction, then Q's this equation.
That makes sense.
There's one other tricky thing. This is one way of expressing the first law. There's another way of expressing the first law. If you recall, the first law is also delta U is equal to Q plus W. Any change in energy is going to be exchanged in terms of heat or work. So, well, in terms of heat and work, what types of work could we do? Well, there are different types of work. You could run a machine, or drive an engine, or generate electricity. So when we heat up water, did we do any work, or did water do any work? In this case, there was no work done. And so when we're looking at delta U here, delta U is actually equal to the energy exchange in terms of heat. Energy exchange in terms of heat and or work. In this case, there's no work done. And so really there's a plus a W here, but this plus W is 0 here. And so in this case, the delta U is just equal to the heat that's absorbed by this. Over here, it's the same thing. Delta U is equal to Q plus W. But this one's a bit more tricky. This one's a bit more tricky because what do we do about the work? When you burn methane, you could actually do work. If I think I mentioned in the past, if I'm driving and I'm following a diesel bus, if I follow a diesel bus, or diesel car, I hit the recirculation button because I don't want to breathe in diesel fumes, lots of NOx and particulate pollution. However, if I'm following a CNG bus, the CNG bus is clean burning, really pretty clean burning, so I don't turn on recirculation. The CNG burns compressed natural gas. And so it burns that in the engine. So rather than burning gasoline, it's burning methane to drive the engine. In that case, it's doing some work. And so we can burn methane to do work. The CNG bus doesn't completely convert it into work, so it's not 100% work. There's also some heat. It gets hot back there. And so it's heat and work. Heat and work are what we call path-dependent functions. Delta U is called a state function. State functions are path independent. And so this is like $1,000. You know, what can you do with $1,000? Well, it depends on what you want to spend it on. You could take $1,000 and spend it all on heat. Or you could take that $1,000 and try to do as much work as possible. Because of friction, there are going to be some heat losses though. Or it's like a AA battery. If you have a AA battery, what can you do? How much work can you do? Well, it depends. If you have a little fan, you can do lots of work with the AA battery and a fan. Or if you have a little battery-powered heater, then you can do a lot of heat. And so the AA battery is going to have a fixed amount of energy. That fixed amount of energy doesn't depend on the path. It's always the same. Just like when we burn methane, you know, there's going to be a fixed amount of energy. So when we look at U initial is equal to the potential energy initial plus the kinetic energy initial. When we look at U final is equal to the potential energy final plus the kinetic energy final. In this case, when we look at delta U is equal to delta potential energy plus delta kinetic energy. If I look at the temperature here, the temperature stays the same. We go from 25 to 25 degrees C, so the change in kinetic energy is 0. So this is just a result of the change in potential energy. Well, the change in potential energy is going to be fixed, you know, according to, in this case, primarily the bonds here are different. They'll have different energies. So the amount of energy in this process is fixed, but the amount of heat we generate depends on how much work we do in this reaction. The more work we do in this reaction, the less heat we get. Because delta U is equal to Q plus W. And what we need to do is try to do no work for this. If we do no work, then we convert all that delta U into heat. And if we can convert all that delta U into heat, then we can use that heat to warm up the water. And so how can I do no work on this particular reaction? Well, it depends on the types of work that we have. Did I talk about the types of work? Okay. Well, we're not going to hook this up to electrical generator. Actually, that's one of the big things. You know, out west, most electricity is produced by burning methane. Now, back east, most electricity is produced by burning coal. So, we're not going to hook this up to an electric generator and do the work there. In fact, what we're going to do is we're going to try not to do any work, but there's one type of work that's hard to avoid. And so the work term is going to equal the work, which we'll call PV, plus the work, which we call electric, plus the work, which we call mechanical, plus ... whatever else we can do. Well, this first work here, this is called the natural work of a chemical reaction. Or process. The natural work is changes in volume. Did I already talk about blowing up the balloon? If I have a balloon and I want to blow it up, how much work does that take? So if I have a balloon and I want to blow it up, the amount of work is going to equal how big of a balloon do I want to blow up. Not only that, it's going to depend on how much pressure I have to fight in order to blow up that balloon. And so the amount of work it takes to blow up a balloon depends on the external pressure times delta V, how big the balloon is. So if I blow up a balloon at the bottom of the ocean where the pressure is quite high, it's going to take more work than if I blow up the balloon, let's say, at sea level. And the bigger the balloon, the more work. There's a sign convention for work as well, and that is this. If you lose energy doing work, that is, work is less than zero. If we lose energy doing work, this is going to be like exo, but it's not heat. And so what we say is work done. And so if you had to do work, then you're going to lose energy. Well, the pressure is always positive, and if you're blowing up a balloon, it's going to grow bigger, so V final is going to be greater than V initial. So we have to put a negative sign here, otherwise it's the wrong direction. And so if the work is less than zero, work was done. So what we're going to do is we're going to blow up. Let's blow up a 1 liter balloon. I'll just say delta V is equal to plus 1 liter against a pressure of 1 atmosphere. How much work was done? Well, the amount of work that was done is going to be pressure 1 atmosphere, volume change is 1 liter. Well, it's going to be 1 liter atmosphere. Well, that's weird because a liter atmosphere is not a normal unit of work. Do you know the conversion from liters atmosphere to a normal unit of work? Did I talk about that yet? No? If you ever forget it, it's easy to derive. And that is, do you know the R values? There are 2 units for R. What are they? This is the gas constant.
0.08206.
Yeah, 0.08206 liters atmosphere per mole Kelvin. And this is equal to the other unit, which is .314.5 joules per mole Kelvin. And so liters atmosphere is a unit of energy. And in fact, we can relate liters atmosphere in joules. How can we do that? Well, we just do this. We take 8.3145 joules per mole Kelvin on the top, and then underneath we'll put 0.08206 liters times atmosphere per mole Kelvin. The moles cancel, the kelvins cancel, and that leaves me with joules per liter atmosphere, and it comes out to 101.3 joules for every liter atmosphere. And so to blow up a balloon, a 1 liter balloon with an external pressure of 1 atmosphere is going to take 101.3 joules of work. So it takes about 100 joules to blow up a 1 liter balloon. Now, am I losing energy or am I gaining energy by doing this? I'm losing, so I have to pay attention to the sign convention. So this has got to be negative, negative, negative. So negative 101.3 joules means I'm losing that much energy. But where's that energy going? Because the first law of thermodynamics says that the energy is conserved. It can neither be created nor destroyed, so that energy has to go somewhere. Well, that energy went into blowing up the balloon, didn't it? And so if the energy went into blowing up the balloon, then the energy's gone. Is that correct? I mean, let's say you spend $20, that $20 is gone, or is it really gone? Now that $20 actually went to somebody, right? It just didn't vanish into thin air. I mean, you lost it, so you no longer have that $20, but now somebody else has that $20, correct? And so, if you did, and this is kind of weird because you think, well, didn't I just use all that energy to blow up this balloon? Blowing up a 1 liter balloon? And so I consumed this amount of energy. So if I consumed it, right, then isn't it gone? It's like, if I consumed a candy bar, then it's gone. I just digested it and used it, right? And so it seems that way. It seems like, okay, if we use that, it's gone. But it's not really gone. This is not like a candy bar that you just digested. This 101.3 joules went where? This is the first law of thermodynamics. It's going to go to somebody else, and that somebody else we call the surroundings, because we don't know what it is, we just call it the surroundings. So oddly enough, if you spend 101 joules blowing up this balloon, do you know who gained that 101 joules?
Is it the balloon?
You would think it's the balloon, but it's the, kind of weird, but work of the system is equal to minus work of the surroundings. So if the system loses 101 joules, the surroundings gains that. And so the energy, it's kind of weird to think about, but that energy's not gone. The energy went into the surroundings. And likewise, let's say the surroundings blew up the balloon. And so not you, but your friend. Your friend blows up the balloon. You think, okay, now the balloon is blown up. And your friend spent 101 joules to blow up the balloon. And you think, okay, your friend just spent 101 joules, but you're the surroundings. You're the only thing else in the universe. You know what? You're going to get that 101 joules, although it's not like a person to person. The surroundings would be everything. The lab, whatever else. And so, if work was done, we lost energy. But the work was done on something. So if W of the system is negative, then W of the surroundings is positive. And if W of the system is positive, then that energy must have come from the surroundings. And so it's a little bit weird in terms of work. And so when we're looking at the water, no work was done. No PV work was done. Because if we have 50 grams of water, that's 50 milliliters initial, and we have 50 grams of water final, that's 50 milliliters final. So 50 milliliters and 50 milliliters, there's no change here. And so in the object, there was no work done. So delta U is just equal to Q. In the second example here, we have to look at the volumes now. If we look at the volume here, 1 mole of gas at 25 degrees C, so 1 mole of methane at 25 degrees C occupies about how many liters? Yeah. Just roughly, let's say 25 liters. And so 1 mole of methane is 25 liters. 2 moles of oxygen is how many liters? 50. So altogether we have 75 liters of gas here. Then we go down here. 1 mole of CO2 gas is going to be 25 liters. And then we have 2 moles of liquid water. 2 moles of liquid water, is that 50 liters? No. 2 moles, 1 mole of water is 18 grams. So 2 moles will be 36 grams. 36 grams of water is 36 milliliters. 36 milliliters is 0.036 liters, or about 0.04 liters. So we're going from 75 liters, this is about 75 liters, to about 25 liters. 25.04, which will just round to 25. So what happened to the volume? When we look at delta V is equal to minus 50 liters. So the volume here shrank by 50 liters. If the volume here shrank by 50 liters, what happens to the volume of the surroundings? It must have increased by 50 liters. So that means the surroundings must have blown up a balloon by 50 liters. 50 liters would be, 50 times 100 would be 5,000 joules. So the surroundings did 5,000 joules worth of work. Well, that's fine. The surroundings could do 5,000 joules of work because its volume expanded. But what became of that energy? Well, the first law of thermodynamics says that the energy is neither created nor destroyed. So where did that 5,000 joules go? The 5,000 joules goes into the system. So if we burnt a mole of methane, we're going to get an extra 5,000 joules. The extra 5,000 joules comes from the surrounding universe. And so here, delta U is equal to Q plus W. Well, there's going to be some work done. This is what we call constant pressure. In order to maintain constant pressure, the volume has to be able to expand and contract. However, we could do this under constant volume conditions. Under constant volume conditions, let's say we start off at 75 liters, and then we got to finish at 75 liters. So that delta V here is 0. If delta V is 0 liters, then that means, was any work done? No. And so here, over here, work is equal to 0. Over here, under constant pressure conditions, work is going to be, okay, now it's going to be positive because we're gaining it. And so it's going to be minus P delta V, but delta V is 25 minus 75, which is minus 50. So this is going to be 1 minus 1, we'll call it 1 atmosphere. 25 minus 50 liters, which is going to give us plus 5 kilojoules. So what this means is this. This means we get 2 different energies depending on if we do this under constant pressure or constant volume. If we do this reaction under constant volume, then delta U is equal to Q plus W. Under constant volume, the volume can't change, so nobody blows up the balloon. And so delta U is just equal to Q. We call this Q sub V to indicate that it's occurring under constant volume conditions. If we do this under constant pressure conditions, delta U is equal to Q plus W. This is for methane. If we do this under constant pressure conditions, then W is not zero. In this case, W is, well, it depends on how many moles. In this case, I burned 1 mole of methane. And so, And the amount of work done depends on how many moles of methane you burn. If you burn 2 moles of methane, you're going to have a different amount of work done. And so this is turning out to 5 kilojoules per mole of methane that was burned. And so oftentimes we interchange between extensive and intensive representation of, these. In this case, I'll make it intensive because, I want to change it. I don't need to burn. Actually, I don't need to burn a mole of methane to get that much energy there. So this is going to change the amount of energy here, which means I get a little bonus of energy here. And so I have to be aware if I'm burning it under constant pressure, constant volume, because I'm going to get different amounts of heat. Well, this is a graph just showing that we keep the temperature the same. Initial temperature and final temperature the same. This is an exothermic reaction. So we burn the methane at 25, gets hot, and then we wait for it to cool down, 25. And all that energy is released to the surroundings. This is endothermic here. The reaction happens, it sucks energy from the surroundings, and then we wait for it to go back.
This was a little backtrack, but for the balloon example, blowing up the balloon, is the system the person blowing up the balloon, or both?
The system is the person blowing up the balloon and the balloon. The surroundings is also the balloon and whatever else is there. We'll look at it in more detail later. But when we're dealing with measurements, we use a calorimeter. We have 2 types of calorimeter. We have the constant volume calorimeter. This is called the bomb calorimeter. In a bomb calorimeter, you use a heavy-duty metal container here that can withstand low pressures and high pressures. When we lose 50 liters of gas, that's going to generate a vacuum, and we run an implosion risk. If we gain 50 liters of gas, we generate high pressures, which creates an explosion risk. So this bomb has to withstand very low pressures and very high pressures, so it doesn't implode or explode. And so that's why they call it the bomb, because if the pressure gets too great, and it explodes and causes some damage. All right, so here, the situation though is the volume can't change. If the volume can't change, then we can't do any work, at least the natural work of a chemical reaction. And there's nothing mechanical in there, so we can't do any other kinds of work. And so any kind of internal energy change here is going to be all in heat, no work. The other type of calorimeter is a constant pressure calorimeter. This is a constant pressure calorimeter here. The coffee cup calorimeter, this is what we used. But if gas is formed here, then some gas can leak out here so the pressure can be maintained. Or if gas is consumed here, some gas can leak in here to maintain constant pressure. Now, if we're going to burn methane, what do you think is going to be easier? Burning it in the coffee cup calorimeter, which is a constant pressure calorimeter, or burning it in the constant volume calorimeter, which we call the bomb calorimeter? What do you think is going to be easier to burn the methane in? In the bomb. And so what I need to do is I need to figure out, how much energy, what is this potential energy change? Because I'm not going to be able to calculate the initial potential energy and the final potential energy, but I can measure the potential energy change. Now, if I do this in a bomb, there's no work done. So if I do this under constant volume conditions, then delta U is just equal to Q sub V. And so I can just measure, all that heat goes somewhere. And so if I burn this stuff in a bomb, I'm going to convert all that internal energy into heat. And that heat is going to warm up the bomb. So I'm going to burn this. All that change in internal energy gets converted into heat. And so what's the heat going to warm up? The heat's going to warm up the products of combustion. So the CO2 gas and the liquid water is going to get warm. Okay, it's going to warm up the container here, which is just a steel container. It's going to warm up everything in here. There's an igniter. There's water surrounding this. There's a stir thermometer, another case, the lab bench, the air around this. So all that heat's going to dissipate into this, what we call the bomb. The bomb is everything, the rest of the universe here. And so our reaction here happens. We burn the methane. It generates heat. That heat goes into warming up the bomb. So we can figure out, how much heat is generated per mole of methane combusted. In other words, we can determine what delta U is, the internal energy change, quite accurately using bomb calorimetry. All right, but the problem is how many grams of water is this? We need to know how many grams of water, how many grams of steel, how many grams of platform, stirrer, thermometer. Do you want to weigh this thing out? Do you want to determine all the specific heats of everything? No. We don't want to do that. In other words, we're not going to use specific heat. What we're going to do for this one is we're going to use heat capacity. Heat capacity is the easiest way of doing it. These are the common units of heat capacity. C is just heat capacity. And so the most common units would be, let's say, joules per gram degree C. This we call specific heat. And then we have joules per mole degree C. So rather than doing it per gram, we do it per mole. This is called the molar heat capacity. All these are heat capacities. And they all have the same symbol. They just have different units. C. Molar heat capacity. But sometimes when we're dealing with things that we don't want to weigh, we look at the heat capacity of an object. And so this would be the heat capacity of an object. So let's say you're building a brick wall. Do you want to weigh how many grams of brick you have? No, you probably just want to know how many bricks there are. Are there 1,000 bricks in the wall or 100? And so this could be joules per brick per degree C. Or, we only use one bomb. If there's only one bomb, then it's going to be joules per degree C because we have just one bomb. And so most of the time, we'll never have two bombs, so we'll just call it joules per degree C. And so that would be the other unit. This. But do you think all bombs are exactly the same? No, every bomb is going to have a different heat capacity. And so before we can use a bomb, do you know what we have to do is we have to do something first. We have to calibrate the bomb first. And so before we even use this, we got to calibrate it. We got to know, how much heat does it take to increase the temperature of the whole bomb 1 degree C. And so before we can burn our methane, we got to make sure we calibrate our bomb. Because we need to know the heat capacity of the bomb. So if we look at the calorimetry problems here, they say a sample gives off 5,228 calories when burned in a bomb calorimeter. The temperature of the calorimeter assembly increases by 4.39 degrees C. Calculate the heat capacity of the calorimeter in kilojoules per degree C. So 5,228 calories increase the temperature by 4.39. So we take this divided by that, that gives us the calories per degree C. Per bomb. There's only one bomb. But what we need to do is we need to change calories to kilojoules. So we'll go calories to joules, joules to kilojoules. But where did this 5,228 calories come from? That we have to figure out. Here, if we look at the next problem, 36, the following substances undergo complete combustion in a bomb calorimeter. The calorimeter assembly has a heat capacity. So they give us the heat capacity, so this has already been calibrated. For this particular bomb, in order to increase the temperature of the bomb by 1 degree C, it takes 5.136 kilojoules worth of energy. So the heat capacity of the bomb is given. Here, they give us the heat capacity of the bomb. Here, bomb calorimetry. The heat capacity of the bomb calorimeter is 4.728. So this one takes slightly less. 4.728 kilojoules to heat or warm it up by degree C. I think that's slightly less. Yeah, so. This is a coffee cup calorimeter. We calibrate those also, but we're looking at bombs right now. This is styrofoam cup, so that's coffee cup. Coffee cup or constant pressure calorimetry. Here's a bomb calorimetry experiment. This is for calibration, 41. 42 is also for calibration. Let's look at 42. Salicylic acid, C7H6O3, has been suggested as a calorimetric standard. So for example, a primary standard, what criteria does a primary standard have to meet? Primary standards must what?
You have to be able to like purchase large amounts of it.
Yeah, it has to be readily available.
Yeah.
Salicylic acid is readily available, preferably cheap. Salicylic acid is pretty cheap. Salicylic acid is the first generation of aspirin. It was a little too harsh on the stomach, so they modified salicylic acid. Modern day aspirin is less acidic. So you have to be able to purchase it. Anything else?
Purchasing high purity.
It has to be in high purity, so it's got to be easy to purchase at high purity. So it's pretty easy to purify salicylic acid. You can buy this at very high purity. Anything else?
It has to be stable.
It has to be stable. Stable means even like hydrate formation, like oxalic acid dihydrate, that's a stable dihydrate. So we don't even bother drying that. Remember when you used the oxalic acid dihydrate in titration? Did you dry that and cool it down in a desiccator? No, otherwise that would have been a hassle. And so what we have is a very stable hydrate, oxalic acid dihydrate, and there's a maximum amount of water that's absorbed in there. And it's pretty stable. So it's either got to have a stable hydrate or a stable anhydrate, or anhydrous form. Anhydrous means it doesn't pick up water. So salicylic acid may not pick up any water, so we don't have to dry it. Or, we don't factor in how much water. Some things pick up varying amounts of water, depending on how humid it is. So this is, readily available and high purity and stable. And so that's one of the reasons they're looking at it as a standard, the primary standard for bomb calorimetry. Its heat of combustion is known to 4 sig figs here or more. And so that's also good. We need to know how much heat we're going to get by burning a mole of this stuff. From the following data, determine the heat capacity of the bomb calorimeter assembly. That is the bomb, water, stir, thermometer, wires, and so forth, everything. And so we're going to burn 1.201 grams of salicylic acid in this. So 1.201 grams of salicylic acid. Salicylic acid is C7 H6. O3. Salicylic acid is a solid acid, and we're going to burn it in O2. This is going to form CO2 and water. Actually, we don't even have to balance this because they tell us the heat of combustion. This is heat of combustion per mole of salicylic acid. So it doesn't matter what the other stuff is as long as we have enough. You know, limiting reagents typically salicylic acid anyway. Even though we don't have to balance it, we'll go ahead and balance it. So we have 7 carbons, so that's going to give us 7 CO2s. 6 hydrogens, we'll need 3 H2Os. And 7 times 2 is 14, plus 3 is 17 oxygens in the product. We need 17 oxygens in the reactant. So we'll need 7 O2s. 7 times 2 is 14, plus 3 gives us 17 oxygens. So we have our delta U here. Our delta U is equal to minus 3.023. We're doing this in a bomb, constant volume. And actually, I should have done something before this. Let's write it up here. Delta U is equal to Q plus W. Can we do any work inside a bomb? No. No work is done inside a bomb. So W is equal to 0 when we're at constant volume. I'm going to show that we're at constant volume by writing Q sub V. And so this is minus 3.023 times 10 to the third kilojoules per mole. Is that the amount of heat I'm going to get? Yeah, that's the amount of heat I'm going to get if I burn a full mole of salicylic acid. But do you think 1.2 grams is a full mole? No, it's way less than a mole. And so this is where it becomes a little tricky because we switch from intensive to extensive without really doing the math here. And so here, technically, this is not true. This is only true if I'm burning a full mole. Delta U is equal to Q if I burn a full mole. In reality, when I look at QV, the amount of heat is going to depend on the amount. If it's a full mole, yes, I'm going to get that amount. But if it's less than a mole, I'm not going to get that amount. And so it's going to be amount times delta U. And so this QV is in terms of per mole. This QV is in terms of just amount of heat. So this QV is kind of intensive, this QV is extensive, but we just represent them all kind of the same. So how much heat am I going to get? Well, it depends on the amount. Well, I have 1.201 grams of salicylic acid. I'll just call it SA for salicylic acid. And then, well, this is the molar, kilojoules per mole, so I need to go from grams to moles. And so let's go ahead and calculate the molar mass of salicylic acid. I have 7 carbons, so that's 7 times 1201, which is 70, 84, 84.07. Is that right? Yeah. I have 6 hydrogens. So that's 6 times 101, so it's going to be 606. I have 3 oxygens, 3 times 1600, it's going to be 4800. And that's going to give me 132.13 grams per mole. So 1 mole of salicylic acid weighs 132.13 grams. And so how many moles is that? Let's take a look. It's 1.201 divided by 132.13. 0.009. Is that what you guys get? 0.009? Not much. We're going to get a lot less heat than that up here. All right, times minus 3.023 times 10 to the third kilojoules, or 3,023 kilojoules per mole of salicylic acid, assuming that we have plenty of oxygen. You know, salicylic acid, it's got to be the limiting reagent here. So times 3,023. I get 27.4, how many sig figs am I allowed? 4 sig figs, 27.477 kilojoules. Okay, this is negative, which means we're going to lose that. Let me just double check that calculation. Yeah, 27.477 kilojoules. Negative. So where's all that heat going to go? All that heat is going to go into the surroundings. The surroundings in this case will be the bomb calorimeter assembly, which we'll just call the bomb. And so we're going to have a bomb here. The bomb is going to start off at initial temperature at 23.68 degrees Celsius. And then it's going to absorb this amount of heat. So if this loses 27.47, then this must gain that. And so delta U here is going to be plus 27.47 kilojoules. And when that happens, we're going to end up with a bomb that's going to be a lot warmer. This bomb is going to be at 29.82. And so the temperature of the bomb is going to increase due to absorbing that heat. Oh, actually, it should be the same. It's not quite the same scale, I think. What happened to the temperature here? Well, initially this must have been at the same temperature as the bomb. It would be 23.68 degrees C. What's the final temperature of this going to be? Is the final temperature of this going to be 29.82? What do you think? It turns out no. The final temperature of this is going to be at 23.68. So the initial temperature and the final temperature are the same. So this starts at 23.68, and then I wait for it to cool down. You know, I would wait for this to cool down. All that energy goes into warming up the bomb, so it's going to hit a peak, a max of 29.82, and then it'll start to cool down as well. Can any work be done inside a bomb? No, no work can be done. So this is equal to Q plus W. W is going to equal 0. The volume doesn't change. So this is just equal to QV. Now, when we're dealing with a reaction or process, you know, Q, this is for QV for reaction, is equal to amount times delta U. However, this is not a reaction or process. This is Q of an object. Q of an object is equal to what? It's equal to the amount times C times delta T. And so it's a different equation for the Q. When we're dealing with a reaction or process, it's the amount times delta U of that reaction or process. This is delta U for the reaction here. When we're dealing with an object, the object is either going to warm up or cool down, so it's just QV of the object. V of the object is equal to amount times C times delta V. Well, how many bombs do we have? We only have one bomb times C times delta T. Delta T, we know, that's T final minus T initial. And so the only thing we're missing is C. So here C is going to equal Q over the amount. Or no, sorry, not the amount. Amount's 1. Q over delta T. So Q is going to be plus 27.47 kilojoules, and delta T is going to be T final minus T initial, 29.82 minus 23.68 degrees C. So 29.82 minus 23.68 equals 6.14. So this is equal to 27.47 kilojoules over 6.14 degrees C. Sorry, 477 or 48. Which gives us 4.475 kilojoules per degree C, which is equal to 4.48 kilojoules per degree C. This is only 3 sig figs. It should have been to 4 sig figs. They should have burnt more salicylic acid. If they burned more salicylic acid, the temperature would have increased more than 10 degrees. If we could have gotten the temperature to increase at least 10 degrees or more than 10 degrees, we would have gotten a delta T of 4 sig figs. If we got a delta T of 4 sig figs, then we would have 4 sig figs in our bomb calorimetry calibration. This is only 3 sig figs. So they should have burnt twice as much salicylic acid. It would have been better. And then we could have gotten the heat capacity of the calorimeter. This. All right, so now once we get the heat capacity of the calorimeter, then we can take something unknown like methane and put in, let's say, 10 grams of methane in there and burn it with excess oxygen and figure out how much did the temperature rise. And then from that, we can get how many kilojoules. And that's going to be the kilojoules for 10 grams. And we can figure out, well, if there's the kilojoules for 10 grams, we can figure out how many kilojoules it would take to burn a mole. A mole is 16 grams. And we can get kilojoules per mole for something like methane. So the first step is to calibrate the bomb. Once we calibrate the bomb, then we can figure out the heat of combustion of different substances. An example would be something like xylose. Here. Or methane. Or whatever we want. All right, so here they put some xylose, which is a solid C5H10O5, 1.183 grams, and they burn it. And then they figured out how much the temperature increased, delta T. From this delta T, that gives us the degree C, we can figure out how many kilojoules from the heat capacity. Once we know how many kilojoules, that's the number of kilojoules for this many grams. And then we can convert that from kilojoules per gram to kilojoules per mole by converting grams into moles. And then we get the heat of combustion of xylose per mole. Now, when we look at heats of combustion, we have to be careful because we have two types of heats of combustion. We have heat of combustion under constant pressure and heat of combustion under constant volume. The amount of heat depends on how much work is done. The more work, the less heat. And so these might not give the same values. And so we have delta U, and we have delta, we have another symbol for it. So delta U will be the amount of heat under constant volume conditions. And we have something else called delta H. Delta H will be the amount of heat under constant pressure conditions. And so this is a new symbol that we have. Delta U is the change in internal energy. Delta H is the change in enthalpy. And so this allows us to differentiate this. So when we're looking at heats of combustion, we want to know, is it a delta U or is it a delta H? In other words, is it constant volume or is it constant pressure? That's because they'll give different amounts of heat. Sometimes the heat is almost the same. For example, in salicylic acid, it says heat of combustion. Is that under constant volume or is that under constant pressure? Did they tell us? They tell us that it's in a bomb, so I'm assuming since this is a bomb, it's got to be constant volume. And therefore that heat of combustion is a delta U. Does that make sense? But for salicylic acid, it's a little bit different. Salicylic acid is a solid. So again, we had C7H6O3, solid. If I have a mole of this weighs about 132 grams. The density of a typical solid is around twice as dense as water, twice as heavy as water. And so the densities of most solids are around 2 grams per milliliter. So if I have 132 grams is roughly about 60 milliliters, roughly 60 milliliters, just a guess. Plus 7 moles of O2 gas. 7 moles of O2 gas is roughly how many liters? 175 liters. This is roughly 175 liters. So if I take these together, the initial volume, B initial, is going to be 175.06 liters. Or about 175 liters. I don't think we can be this precise. So we'll just say about 175 liters. Because the volume of the solid is so small compared to the volume of the gas. Okay, this is going to go to CO2. I'm going to have 7 CO2s. 7 CO2 gases is going to be about how many liters? 175 liters. Plus 3 moles of H2O liquid. 3 moles of H2O liquid is going to be about how many milliliters? Well, 3 moles is 3 times 18. 45 plus 9, 54. This would be 54 grams, which is equal to 54 milliliters, which is equal to 0.054 liters. So V final here is equal to 175.05 liters. So when we look at the density of this solid and liquid, it's not so much. Really, this is going to be dominated by the volume of the gas. I mean, not density, volumes. And so what we're going to say is we're going from 175 liters to about 175 liters. So if we go from 175 liters to 175 liters, was there any change in volume? I mean, there was a very, very small change in volume, 0.06 to 0.05. Is that going to create or require much work? No. Not at all. So if we do this under constant pressure conditions, it's going from 175 to 175, it's pretty much the same. Or we do this under constant volume, it's about the same. And so delta U here, which is under constant volume conditions, is going to be pretty much the same as delta H under constant pressure conditions. Because whether we do it under constant volume or constant pressure, the volume really doesn't change. Does that make sense? And so this is another reason why they want to use this as a calorimetry standard, because it doesn't matter. Constant volume or constant pressure is going to yield the same amount of heat because no work is done in either case. But we're out of time, so I'll stop here and we'll continue with this next time.